Alright, here's a little video about titration, sort of revisit some of the things that we talked about in class. Hopefully you understand titration. You take a solution of a known concentration, which you call the titrant, and that's added to a known quantity of the analyte. And with that information, you can determine the concentration of the analyte. We are going to use this to basically determine the pH at any point along a titration. And that's generating those points are known as a titration curve. Alright, first thing, let's look at titration curve for a strong acid, strong base solutions, and the combination of the two produce a neutral salt and water. So if we look at a titration curve, we've got these points that go along and form this nice little curve like this. And we're going to look at this and think of it in four regions. Region number 1, region number 2, region number 3, and 4. So let's look and see what it is that is in the solution at any point. So thinking about point 1, initially, we're starting with a strong acid, and that's why the pH is so low, adding a strong base to it incrementally. Increasing the pH is why you see the pH increase as the volume of the titrant increases. So initially, starting at this first point, initially all that's present is acid, so strong acid. Then, in this region number 2, as we add base, what's going to be present is still strong acid plus a neutral salt. So the one thing that's going to determine what the pH is at any point in that region 2 is how much excess strong acid there is. In region number 3, at that we call the equivalence point, where the number of moles of the strong acid equals the number of moles of the strong base. And because that is a stoichiometric, they are stoichiometric quantities, then all of that acid and the base have been consumed to produce a neutral salt. And a neutral salt is just that. It's neutral, pH 7. And so region 3, the only thing that is present is the neutral salt. In region 4 here, after we have consumed all of the strong acid, so strong acid has been converted into the neutral salt, if we continue to add base, what's going to be left is just excess strong base. And so knowing the quantity of strong base in excess will allow us to determine the pH. And here in those four regions, directions for determining the pH at any step with a strong acid, strong base titration. The first region, you just take the negative log of the initial acid concentration. In region 2, you figure out how many moles of acid are in excess, divide that by the total volume, to be the volume of the acid initially plus the volume of the base that's been added, and that gives you the concentration of the excess acid, and take the negative log of that. In region 3, remember this is a strong acid, strong base, so it produces a neutral salt. So region 3, at the equivalence point, the pH is always going to be 7. And then in region 4, we're just looking at how much excess base is left, and so we determine the quantity of excess base, divide that by the total volume to get the molarity of the base, and then we take POH minus pH to get the pH. Wait, POH, excuse me, we take the PKW minus the POH, minus POH, and that gives you the pH. Alright, so this problem, sample problem, we're going to take 50 milliliters of 0.2 molar hydrochloric acid, titrate it, and we're going to titrate it with 0.30 molar sodium hydroxide. I want you to be able to calculate the pH after adding 20 milliliters of the base at the equivalence point and after adding 50 milliliters of the base. Now I'm going to work with the millimoles because that's just a little bit easier. So if you take the volume in milliliters and multiply it by the concentration in molarity, you get volume in milliliters, concentration in molarity, you get millimoles. And so starting out with 50 milliliters of 0.2 molar HCl, that means we're initially starting out with 10 millimoles of HCl. And then if we start and we add 20 milliliters of 0.30 molar sodium hydroxide, that means we have added 6 millimoles of sodium hydroxide. Now remember that this is HCl plus NaOH, and it produces salt, NaCl plus water. If we start out with 10 millimoles of that, and we add 6 millimoles of that, we're going to consume 6 millimoles of the HCl, consume 6 millimoles of the NaOH. We're going to produce 6 millimoles of NaCl. Now NaCl is a neutral salt, so what are we left with? We're left with 4 millimoles of hydrochloric acid, and that is going to be in a total of 70 milliliters. So that gives us a concentration of 0.0571 molar hydrochloric acid excess. And if we just take the negative log of that, you get pH equal to 1.24. Next spot, let's go ahead and calculate the pH at the equivalence point. Easy enough, strong acid plus strong base. At the equivalence point, pH equals 7. Now, can you determine the volume? I know it's not asked for, but let's determine the volume of NaCl, or excuse me, of sodium hydroxide required to reach the equivalence point. And that's easy. That's just stoichiometry. And so we could say we start with 50 milliliters of the HCl, and we multiply that by its concentration, 0.20 moles of HCl per liter. And we know that we are going to consume 1 mole of HCl for every 1 mole of NaOH. And our sodium hydroxide concentration is 0.30 moles of NaOH per 1 liter. And if we cancel out units, moles of HCl, moles of sodium hydroxide, liter, we're left with units of milliliters. And the volume of sodium hydroxide needed to reach equivalence point is 33.33 milliliters. Just a nice little bit of information. All right. Next slide, we want to calculate what is the pH after adding 50 milliliters of base. Now, note, remember we started out with 10 millimoles of HCl, 50 milliliters of base, that would be the volume in milliliters times concentration in molarity, gives you 15 millimoles of NaOH, and that NaOH will consume all the HCl, and you'll be left with 5 millimoles of NaOH. If we want to know the pH, we've got to take that 5 millimoles of NaOH, divide that by the total volume, which is 100 milliliters, and that should give us a concentration of 0.050 molar, and that's molar OH ions. And if we take pH is equal to 14, the pKw, minus the pOH, negative log of our concentration of OH, 0.050 molar, you come up with a pH of 12.70. Alright, here in part 2, let's look at or visit what happens during a weak acid and a strong base titration. And in this case, we're starting out with only weak acid, and as we add the titrant, the sodium hydroxide, the pH increases as we would expect it. And we're going to be breaking this up into 4 main regions, just like we did with the strong acid, strong base. In our first region, in this spot, this is the initial pH, and initially, before we've added any of the strong base titrant, all that should be present is the weak acid. As we add strong base, we will be consuming some of the weak acid and producing some of its conjugate base. So in this region number 2, then what we will have present is we'll have some of the weak acid and some of its conjugate base. In this case, this would be a buffer system. Then at the equivalence point, we will have added a stoichiometric amount of the strong base to convert all of the weak acid into its conjugate base form. So at this point, the pH would be dictated by the equilibrium of the conjugate base and its interactions with water. And finally, after the equivalence point, then we will, if we continue adding strong base, then we will have an excess of strong base, and its excess quantities will determine the pH. Alright, so how do we determine the pH? First region, and this is an equation that comes from the ice table we've derived in class a couple times, but that the pH is equal to the negative log of the square root of the Ka times the initial concentration of the weak acid. Now this, remember, is assuming that X is small. In our buffer region, region 2, we will use the Anderson-Hasselbalch equation, and its most convenient form for this case is pH is equal to pKa plus the log of the quantity, the moles of base, divided by the number of moles of acid. In region 3, now remember, we've converted everything into the A- form, and that conjugate base plus water can reform some of the acid and OH minus, and it's this equilibrium, this production of hydroxide, this fact that the conjugate base acts as a base and forms hydroxide will cause the pH to be at equivalence above pH 7. And so to determine the pH, we take pH is equal to 14, which is pKw, minus the pOH, and the pOH is found by taking the negative log of the square root of the quantity Kb times the concentration of the conjugate base. And again, this is making the assumption that X is small. And in the region 4, where all we have is excess hydroxide, we do pH is equal to pKw minus the pOH, and the pOH is found by figuring out how many moles of hydroxide are in excess and divided by the volume total, and then taking the negative log of that. And finally, this one little point right here, that is at the half equivalence point, and that's where the moles of base equal the moles of the conjugate acid, and at that point pH is equal to pKa. Alright, sample. We're going to take 50 milliliters of 0.20 molar weak acid, and generically, and then just it's got a Ka of 1.0 times 10 to the negative fifth, and it's titrated with 0.30 molar sodium hydroxide. We want to calculate the pH after we've added 20 milliliters of the base at the half equivalence point and the equivalence point, and then finally after we've added 50 mils of the base, which is in excess. So initially, if we are starting with 50 milliliters of 0.20 molar weak acid, you can put that into your calculator and find that that makes 10 millimoles of HA. And by adding 20 milliliters of this 0.30 molar base, that means we've got 6 millimoles of NaOH. Alright, so if we look at our system HA plus our sodium hydroxide, we are going to just assume that the sodium is a spectator, and that's going to produce H2O plus A minus plus Na plus. Alright, so starting with 10 millimoles of that and 6 millimoles of that, we'll consume 6 of the acid and produce plus 6 millimoles of the base. So what we're left with is 4 millimoles of the acid and 6 millimoles of its conjugate base. Buffer system, and we'll say then the pH is equal to the pKa plus the log of the moles of the base, 6 moles, divided by 4 moles, pH equals 5.18. Find at the half equivalence point. So what is the equivalence point? To determine that, we need to use a little bit of stoichiometry to determine what volume of the stoichiometry, what volume of the titrant would be necessary to reach that half equivalence point. But that's not necessary to answer this question. If we wanted to just find the pH at equivalence point or half equivalence point, pH is equal to the pKa, and so pH would equal 5. Now, what volume is the half equivalence point? That might be a good thing to think about. And to determine the volume of the equivalence point, we could do that just like we did with the strong acid, strong base, using a little bit of simple stoichiometry, starting with the 50 milliliters of the HA. We know its concentration was 0.20 moles per liter. And then for every 1 mole of HA, we need 1 mole of the sodium hydroxide. And our sodium hydroxide was given in a 0.30 moles per liter. And that means to reach equivalence, it is 33.33 milliliters. So the volume at the half equivalence point would be half of that, which is, what is that, 16.67. So the volume at the half equivalence point is 16.67 milliliters. After we've added that much of the titrant, the pH should be 5.00. Let's determine the pH at the equivalence point. Recall from the previous slide, we determined the equivalence point would require the addition of 33 milliliters of the base to reach equivalence point. And that if we started with 50 milliliters of the 0.20 molar acid, and that would be 10 millimoles of the HA initially, and at the equivalence point we have converted that to its stoichiometric amount, 10 millimoles of the conjugate base. Now that conjugate base in an equilibrium with water that we'd already drawn to regenerate the acid form plus some OH minus. To determine the pH at this point, we take pH is equal to the pKw 14 at 25 degrees Celsius minus the negative log of the square root of Kb times the concentration of the conjugate base. So we've got 14 minus the negative log. Kb is going to be 1.0 times 10 to the negative 9. multiplied by the concentration of the conjugate base, which if we took the 10 millimoles divide by the total volume, the 33 milliliters of the titrant plus the 50 milliliters of the acid, 83 milliliters. And we cannot forget to take the square root of that quantity, plug that into your calculator, and your pH hopefully will equal 9.04. And finally, we want to figure out what is the pH after 50 milliliters of the base has been added. Again, we started with the 10 millimoles of HA, 50 milliliters of the base. If we take the 50 milliliters times its concentration, we come up with, we've added 15 millimoles of sodium hydroxide, an excess of 5 millimoles of hydroxide present. Now, vast excess of the hydroxide is going to dictate the pH, and we would find that the pH is equal to pKw 14 minus the negative log of the hydroxide ion concentration, which is going to be the 5 millimoles, divided by the total volume, and that'd be 50 milliliters of titrant plus 50 milliliters of the acid, 100 milliliters. Plug that into your calculator, and hopefully you get 12.70. Hope this helps you out. Enjoy titrations. The process is pretty fun if you just think about what you've got and where you're at in the titration curve. Good luck.